Hello and welcome to this virtual OCP session. My name is Ihab Hamadi. I'm a fellow at Western Digital, where I focus on systems architecture. This presentation is about Ethernet attached storage, more specifically NVMe over Fabrics devices and platforms. NVMe over Fabrics has been around for a few years now, and the ecosystem of NVMe over Fabrics is one that continues to mature, which has in turn enabled a number of design choices. And that list also continues to grow. So we now have choices for the type of external and internal fabrics to use, as well as different attach point possibilities. All of that inevitably also presents trade-offs for the different designs that we could have. This presentation will touch on some of those points. In addition to that, the specifications have been evolving, enabling a few different transports that can work on top of Ethernet. Rocky, iWarp, and TCP are now all supported with NVMe over Fabrics. Let's start with some background material. NVMe is a storage protocol that was developed as a modern protocol, in many cases replacing some of the older storage protocols that had some inherent limitations and could not provide the attributes that modern data center elements and architectures from compute, networking, and storage require. NVMe generally supports scalable parallelism through appropriate constructs. For example, an NVMe storage device provides a fairly large number of I/O queues. That is good for multiple reasons. If you think about modern CPUs, you typically think in terms of cores as one of their attributes. Modern applications have multiple threads, multiple processes as well that run on those cores. Those threads and processes run in parallel and can perform IOs to storage and not have to serialize those IOs because the storage has maybe one IO queue or maybe a small number of those IO queues. So this removes bottlenecks around true parallelism. NVMe attempts to remove some cost components by reusing some hardware building blocks. This, of course, can vary from one design to another. NVMe is an efficient protocol that requires minimal processing on the host side within the application and also within the rest of the storage stack. So going through the operating system layers, drivers, and so on. NVMe can generally enable high bandwidth due to its efficiency. Some people and literature actually refers to NVMe as accelerated storage. The next attribute is one that most system designers, software developers, DevOps teams, and support teams all love. NVMe requires one driver for everything. You don't need a set of different drivers per vendor. You don't need to worry about interdependencies and conflicts and so on. It's just one driver, and any NVMe device works with that. Now that we've gone over the benefits of NVMe, let's talk about NVMe over Fabrics. So NVMe over Fabrics takes all the attributes that make NVMe accelerated storage and then puts that on a storage fabric or a network, effectively enabling shared accelerated storage. Let's move on to the evolution of NVMe over Fabric controllers. Starting from the left side of the slide, going back to the early days of NVMe over Fabrics, some of the demos at the time used standard off-the-shelf servers with server-class CPUs, DRAM, and RNICs. The first demos of NVMe over Fabrics were generally NVMe over Rocky. Now, that made a lot of sense at the time that they used standard off-the-shelf servers. The part of the standard that described NVMe over Fabrics, things like capsule formats, the various bindings and so on, did not even exist. So prototyping, all of that on standard servers provided a good level of flexibility. And those were the advantages to that approach. The disadvantages are high cost, high power, and high space requirements. Now let's shift our attention to the middle column of the slide. As is common in technology, we went through a shrink process and two tracks sort of emerged. The first one is one where we have smart NICs or SNICs. Those smart NICs are really, they represent microservers that run on small form factors that look like NICs. Instead of server class x86 CPUs, most of these smart NICs have embedded ARM cores. The second track has FPGAs replacing those embedded ARM cores. And that allows you to do interesting things with data, processing it at really high speed and doing potentially useful things with that, offloading your general purpose compute within the data center so it could focus on running your applications. Now, let's shift our attention to the right column on the right side of the slide. There's another shrink process that took place, this time replacing those general purpose embedded CPU-based smart NICs or FPGA-based smart NICs with ASICs. Those ASICs are extremely efficient at being NVMe over fabric controllers. They generally do one thing and they do it really well, providing low cost, really a fraction of what you would pay for the two previous generations. They provide really high speed, much lower latency due to the fact that the I/O path is generally implemented 100% in hardware. And they generally consume lower power. Those are the advantages. Disadvantages, those ASICs do not offer much flexibility. They function as controllers, but they cannot do general purpose processing of data like you could do with SmartNICs. So which class of these controllers is the right one for your product? I think it's fair to say that the server-based approach is a thing of the past. You won't see much of that in production today. That leaves us with the second and third generation of controllers. Depending on your design objective, things like bandwidth matching may require you to actually have number of these controllers stacked or bundled together to match the bandwidth on both sides. Latency requirements. If you're looking for the absolute lowest latency, the ASIC option may offer you what you need. Now, power and cooling are generally what they are, and they will vary by product. If you require a certain level of virtualization of storage or transformation of data, SmartNICs may be the right way for you to go. And finally, all of these options will clearly have different cost points associated with them. Let's move on to the evolution of NVMe over Fabric's platform. Starting from the left side of the slide, the diagram on the left represents the type of designs you will see over the next 18 months or so, 2020 and 2021 timeframe. The diagram shows an NVMe over Fabrics storage platform that is highly available with two I/O modules. Non-HA designs will have just one of those I/O modules. Now, let's unpack the I/O module and take a look at the main elements. Starting from the Fabric side, what you'll see is either SmartNICs or ASICs providing the interface to the NVMe over Fabrics. Basically, this is your Fabric side. In the case of RNICs, you may see certain level of advanced virtualization features implemented. In the case of ASICs, you will see cost savings, lower latency, almost no virtualization. Both SmartNICs and ASICs have PCIEs on their backends. And you generally have more drives in the platform than what can be addressed by a single controller. So you will see a number of these controllers being bundled together, and then you will see a PCIe switch. And the number of ASICs or SmartNICs will depend on your design goal for the bandwidth matching and oversubscription ratios between the front end and the back end. Now let's shift our attention to the right column on the right side of the slide. Another process that we commonly see in technology is integrate and shuffle. We expect to see that take place here. with current projections being 2022-2023 timeframe. Perhaps prototypes coming out to the market a little bit sooner than that. With this integrate and shuffle process, the drives themselves change their interface from PCIe to Ethernet, and the protocols from NVMe over PCIe, the standard NVMe over PCIe, to NVMe over fabrics. Once that happens, the I/O modules can be simplified. An I/O module will only need to have an Ethernet switch as not the only element, but the most important element within that I/O module. It will also need to have a CPU, most likely a small CPU, to run the control plane for that switch. Front-end interfaces and back-end interfaces will all just go through the switch. This change effectively moves the attach point from the I/O module on the platform all the way to the drive itself. Now, this will even make more sense as you scale the number of drives in the platforms and you start using higher radix Ethernet switches. Let's move on to the evolution of NVMe over Fabric Spec. NVMe 2.0 Spec is undergoing some major restructuring. If you look at the diagram, the middle layer represents the base spec with device-independent NVMe and NVMe over Fabric functions, no transports. The bottom layer represents transports with clean bindings, effectively allowing separation of transports from base functionality and allowing more transports to be added as needed. The top layer represents the different command set specs, with many of them being optional. So in addition to block I/O and admin command sets, you will see things like zone namespaces or ZNS, key value storage, computational storage, and so on. To put it simply, you get to implement what you need, and NVMe will not stand in the way of innovation. Turning our attention to the evolution of NVMe over Fabric command set, which is becoming more flexible and beginning to cover broader areas that were not in consideration in the past. I'd like to illustrate this point by an example of a potential new command set for cold storage, with some early discussion taking place on what might make sense for this. For example, instead of jumping directly to legacy tape constructs for cold storage, maybe we use modern constructs like storage SLAs. Now, let's talk about what all of this evolution in the areas of NVMe over fabrics, controllers, devices, platforms, and spec represent. For the first time, we have all the ingredients needed for true open composability and open composable infrastructure in the data center. NVMe over fabrics being the backbone of interconnects. Disaggregated elements include compute as one type represented by servers with architectures of your choice, shared accelerated storage, which is mostly flash-based, with things like ZNS for control over placement, true multi-tenant isolation all the way down to the low-level flash constructs, as well as noisy neighbor issues going away, all accessible with a single Ethernet-based storage fabric, that is NVMe over fabrics, and a slightly cooler tier with less stringent SLAs, perhaps backed by disk-based storage, and finally another cooler tier for secondary storage with things like legacy tape or new platforms that may be replacing legacy tape. Now, what binds all of this together is the Open Composable API or OCAPI, which is an OCP project that defines the APIs needed to compose virtual bare metal systems out of these composable elements. I will conclude with a call to action. First, support open composability for the data center by building open composable elements. Second, use open standards like NVMe over fabrics in your design whenever possible. And third, as we've seen, a good number of NVMe over fabrics devices and elements come to the market, there is a need that's emerged to have a lab that can test interoperability and compatibility. Anyone can bring their device of choice to the lab, run a set of automated tests with NVMe over fabrics, perhaps try different transports, different oversubscription ratios, among other things. The website for the lab is opencomposable.com, and we'll be working with OCP to see how we can make the lab more readily available through OCP if needed. Finally, review and contribute to Open Composable API or OCAPI. It currently supports various types of devices, compute servers, network switches, various types of storage, etc. And there's a lot of room to add things like new types of accelerators or maybe enhance some of the existing types. Thank you very much for your attention.